Hi, hello everyone. I'm here to introduce you to Google's Swift, a delay-based congestion control for data centers that achieves low latency, high utilization, and near zero loss, which is also implemented entirely on end hosts. Now, this is a very recent work that they published in SITCOM 2020. And after studying the evolution of the internet, this time we get to see the state of the art congestion control compared to those historical designs. Now, hopefully, that you still remember the paper from the first one, the BBR paper that came out 2016. This Swift paper claims to have 3 years of experience, which supposedly would give you a continuous view of their development. Now, to bring us onto the same page about this topic, congestion control is a way to modulate traffic entering a network in order to avoid congestion collapse resulting from the oversubscription, i.e. way too much load on the network. And this is typically accomplished by reducing the rate of packets sent from sender to receiver. And traditionally, we also differentiate the congestion control that prevents sender from overwhelming the network. And also, another thing is the flow control that prevents sender from overwhelming the receiver. But in this work, we're going to see this fine line of differentiation going away, but the essence is still the same. So remember BBR, it uses delay as a sign of congestion within the network as opposed to the packet loss. It tries to accurately measure the round-trip propagation time and bottleneck bandwidth to provide an accurate number of in-flight number in the network that the network can sustain. And as opposed to the ACK clocking mechanism, sending packets back to back as long as the number of in-flight packets is fixed, BBR paces sending packets at a rate so that it matches the bottleneck link departure rate to avoid queue buildup. So all of these from BBR still applies, but some underlying technology changed, which is now inspiring Swift. So the first motivation we have is that a lot of new latency sensitive applications are introduced into Google Datacenter, and also that its media is shifting, and also that those media are heterogeneous. As you can see on the right table here, we have Flash and NVIDIA RAM. Those have the latency that are magnitudes of difference than that of HDD, and they are becoming the norms because their price are going down, and Google is no longer needing HDD as the common storage units. And how these media are usually used is that HDD and SSD usually serve for storage needs for many of applications, and generally they generate throughput intensive traffic, whereas the in-memory key value store are latency sensitive. A second one is that they have dramatically increased the line rate to 100 gigabits per second, and what that means is that the network at a lot of times is no longer the bottleneck. If you know some of the machine learning work, system work, they are now stressing on the I/O bandwidth as the bottleneck instead of network. And what that means is the following two. The congestion could happen both at the endpoint and the fabric, and also that when queue is building up, it could build up really fast, which require a much faster reaction. So from number two, I want to remind you that the old abstraction of a network is no longer applicable. The vase with the thin neck that I showed earlier only applies when network is absolutely the bottleneck, and that's no longer the case here. So some of the main questions that Swift asks is that can we provide a low, tightly bounded network latency, near zero loss, and high throughput while scaling? Now, And also that can we design an E2E congestion control that manages congestions in the fabric and the hosts? And at last is that can we also make it CPU efficient? It turns out that's also important as well. But notice how these are in an order which stress the rank importance for each point. The key idea for the Swift paper is that it tries to accurately measure the round trip time. By that, Swift could react to the instantaneous delay as opposed to the average filtered or low-pass filter delays. They are also no longer delaying any acts anymore. For two is that they are decoupling the host and the fabric delays, keeping two windows being the number of packets allowed in flight, and they keep it for both fabric and endpoint, which they use the lesser of the two to avoid congestion. Number three is that the pacing packet is no longer is not CPU efficient. They found out about that and compared to the ACK clocking. So while the conventional wisdom is that always-on pacing is beneficial in terms of smooth traffic and low losses, but they found that pacing packets for moderate or higher flow rate did not really provide much performance than that of the ACK clock window. So with all of that in mind, let's take a look at how they are managing the first 2 main points. The graph on the right shows you the life cycle of packet going through the network. The top one shows you where they are and where the queue can happen, build up. The bottom one says where they are taking the timestamps. So a packet starts off from the network card transmission side. They consider this first step time to be negligible. Then it works its way through the network. This queuing plus propagation time is captured between T1 and T2. And then it reaches the destination on the other side through its network card, and then do some queuing for the acknowledgement, and then traverse back through the network to the sender, and then take a while maybe to get to the hosts from the network card. So how they're measuring the two things is that the endpoint delay is the sum of difference between T4 and T2, which is the delay happened on the receiver side, and T6 and T5, which is the delay from the sender side, ignoring the first step. The fabric delay, which is happening here, how they are measuring it is to have T6 minus T1, the entire difference minus the endpoint delay to get the round trip time that's spent in the fabric. So why don't they measure anything like T2 minus T1 or T5 minus T4? While it's not explicitly said in the Swift paper, but if you're familiar with the idea of a true time, another idea by Google, hosts within a single data center even, while maintained by the atomic clock, they can have different time, and the difference can be huge compared to the delay that they're doing right now. So this way, they are only deducting the time duration from to extract the duration from the timestamp recorded at the same hosts. Now, the other thing they've done is that they've also improved upon the old additive increase and multiplicative decrease mechanism to compare delay, is the instantaneous delay, with the target delay. The important change in this algorithm here that I want to stress about, I will talk about the target delay in a bit, but the important change is that they're letting the congestion window, namely the number of in-flight packets allowed within a single round trip time, fall below 1. So this solves a incast problem that I haven't really introduced, but I'm going to introduce it now. So what's the incast problem? It's shown in this picture. We have you know how in data center we have the whole non-blocking network that allows literally allows every server to send a full amount of their bandwidth capacity out. But nowhere do we say anything about the inbound traffic, and that creates the problem here. Say if there are enough hosts sending to one destination, say number of hosts or flows is more than the number of in-flight packets allowed, that means at times a flow might not even able to send a single packet in, and by allowing the congestion window to fall below 1 does exactly that. So for example, having a congestion window of 0.5 would mean that one packet flow is allowed to send one packet per 2 times the round trip time. This would help to avoid the incast problem and to avoid the network dropping the packets. So we just talked about comparing delay with target delay. What's target delay is, in my own words, would be the expectation of the delay in an environment without congestion, but everything else is the same. So they break it down into two things. One is that a path could go through several hops, right? So in general, we are not considering in a environment with equal distance between hosts anymore. For data center, the right amount of assumption is that topology is known, sure, but the network distance could be different, but they are bounded at least. So given this environment, Swift translated network path for a flow to a target delay by using the fixed base delay plus a fixed per hop delay, so that it can times the number of hops it needs to get the target delay. Swift also does a second thing, that's a scale target delay with number of competing flows that go through the one pipe. So disregarding again to the incast problem that n number of flows can go through one pipe, and they call this the flow-based scaling. So the graph in below, in the bottom, shows the relation of all of these target delays. On the very bottom, we have the base target. Base target meaning that the minimum target delay required to provide 100% utilization in one hop network with a small number of flows. And then right above that, there's the blue dashed line representing the target flow if we only consider the flow-based scaling. Notice how the value increases as the congestion window decreases from right-hand side to left-hand side. And then, so this highlights the inverse relation of the congestion window and delay. They also, of course, fix a maximum delay allowed so that the target delay does not grow unbounded. And on top of all that, with H bar, the per hop scaling factor times number of hops give you the target delay in the red line that considers both flow and hop-based scaling factor, and Swift uses this as the target delay. So let's take a look at how Google's design do versus other work. So they are comparing Swift with GCN, or better known as Datacenter TCP. It's another congestion control that leverages ECN, the queuing management scheme, which shows on this graph here. Consider this router being a bottleneck. This router would alter the IP header of the ECN bits to provide a feedback to the end host, indicating there's a queue buildup in the bottleneck by a certain threshold value. But what Google claims is that selecting such threshold value is challenging at scale, and especially maintaining it as they grow the data center in even larger. So they use Swift as a way to swap the indication from queue buildup in the fabric to just control the endpoints. And comparing with GCN, they are comparing with another congestion control that are not using loss as an indication, so that to be fair, or have a chance, I guess. Another point to point out before we look at the results is that their experiments are reporting on the combinations of latency or losses and throughput or utilization, because it is essential to deliver all of them at once, but without optimizing one of them at the expense of another. So let's take a look at the first one. Swift wants to they want to show that Swift delivers a low loss rate under heavy utilization. How they're doing that is that by axis they're showing the port utilization. You can think of this as the view of the end hosts in terms of utilization, and then the y-axis being the loss rate. They are showing how Swift is doing really well even at a very high utilization. And then they're showing the same thing, but over here they're showing the queue utilization. So what this means is that this is a way to see utilization from both the end host, which is the port, and within the network, which is the queue that's in the fabric. Now you might notice how there's a spike in the GCN. The paper claims that this is legitimate data, but they just don't know what it was, and they are investigating that. But anyway, in general, this shows that Swift achieves a low loss even at the line rate. Now, the next thing is that they want to show that Swift achieves low latency nearing target delays. They measure the fabric round-trip time across the data center. They show that Swift is able to maintain the average fabric round-trip time around the configured target delay, and controls the tail latency and can control the tail latency much better than GCN. Now the numbers are all aligned on the left-hand side of the base target delay is because that they are normalizing the numbers with respect to the base target delay. Notice how they can only normalize the number of hops, not the number of flows. So the part that's passing the base target delay is due to the large in-cache traffic that triggers the flow-based scaling. So essentially, the target delay is also increasing, but it's not captured by this base target delay. And the next one is that remember how Swift allows congestion window to drop below 1 to combat an in-casting problem? Well, here they did this experiment to show how effective that strategy was. So for throughput, loss rate, and average round-trip metric, they let 5,000 flows against one machine as the destination, and we can see that there's a significant improvement, especially in terms of the loss rate, dropping from 28% to almost nothing. And at last, we're talking about something to interact with TCP here. So fairness of allocation of bandwidth comes in quite well. So at first, they do the traditional test where they start a single flow between a pair of machines, and then they keep the destination machine the same, and then incrementally add one more flow from a different source machine. They add a total of 4 flows, and then they tear them down one by one in a reverse order, and we can see that the flow allocations are tight and fair. In figure 21, they're studying the fairness of 5,000 flows to one destination sharing a single bottleneck link. They plot it against time to show that they are mostly cluttered together without much separation. They also use Jen's fairness index to argue the fairness. Without going into too much detail, Jen's fairness index, the higher the better, the higher the more fair distribution of bandwidth. So also notice that the graph says without flow-based scaling, the FBS, which is again Google trying to argue that the effects of allowing congestion window below 1 helps to tighten the throughput range under extreme demanding workload, and also helps with the fairness. Figure 22 shows the effectiveness of topological-based scaling, the TBS. To remind you what that was, it's a scaling target delay, scaling for target delays based on the number of hops along the path. So they are testing against two flows to the same destination with different paths or origin. This graph shows effectively how TBS can help with the fairness. So with all of that, I guess there are still room for improvement for Swift. One of which is that they are still using the additive increase and multiplicative decrease solution. And one question is that, is there any better incremental functions than additive increase? And what would be the optimal one? The other thing is that if they are hoping to support anything that's smaller than 10 millisecond latency for short transfers, that would require new techniques as the target transfer time then would approach to the actual propagation time in the data center. Next is that they want to ask, can delay be used for a higher level of operations like RPC rate? But to me, what that really is asking is that, is congestion control at the packet layer better than say at an even higher layer? The old E2E argument, can that be applied here? So maybe it could be maybe the congestion control can be done at the message layer, right? And last, they also pop the question of can delay be used for other applications, for example, fine-grained load balancing or timeouts. So that is the Swift paper on top of the BBR, and I would like to know if you have any questions, and or we can have some discussion. Thank you.